Hello, my dear joshful, energetic students. Long time no see. So, welcome back to the series of Noodle Chopsticks. Now, here we usually talk about two ways in which you can solve a problem. You can either go the noodle way or you can go a simple chopstick way. And obviously, the noodle method is very confusing. It is lengthy, it is error prone, and it is very difficult to grasp. But still, you would see many of the teachers use the noodle method. And why is that? I believe maybe they learned it that way. So they don't know there is an easier method out there, or maybe because they want to portray the topic as a very difficult topic so that you can think, wow, if I had not come to this teacher, I would have never understood it. I don't know. Whatever the reason for that is, we are going to stick to the chopstick method. So my name is Bhavdeep Sethi. I have done masters from IIT Bombay. My passion is to convert physics haters into physics lovers. And I always say never memorize anything in physics. Physics is all around you. Look at the nature around you. The physics is all there. The best textbook out there is nature. So never memorize, always learn conceptually. So in today's series of noodle chopsticks, we are going to look at these different types of batteries. You know, all these are rated as 1.5 volts, right? If you look at any of the labels, they say 1.5 volts. So does that really mean I can use this or this or this or this? Obviously, there is a reason that you use double A here because the slot is double A. But what if I didn't have double A batteries? These are double A, by the way. This one is double A, triple A, double A, C, and D. So this is triple A, double A, C, and D. So what if I didn't have a double A battery or triple A battery, whatever is used here? Can I use one of this using wires and all that? Is it advisable to interchange these batteries? Because after all, each of them is 1.5 volts. So what is the difference? So today we are going to understand that using the concept of internal resistance. See, this is how you should learn physics. It's not like you just memorize the formula for internal resistance and get full marks in the exam. That's not how you should be learning. You should be learning with the practical usage of the things. Now, before we start that, let's go through some of the prerequisites. First of all, what is potential drop? Potential drop. This is just a recap, assuming that you already know Ohm's law and all. So let us say there is a resistor here. So let's say this resistor is 3 ohms. Or let's take it 2 ohms. That will be easier for me to explain. So let's say this is 2 ohms. And now let's say I plug in a battery of 6 volts over here. So this battery is 6 volts battery and I'm plugging in 2 ohms of resistance. Now what would happen is the electrons go this way, but the conventional current goes from positive to negative. So we'll say, okay, Ohm's law tells us that V equals IR. So that tells me the current would be voltage divided by resistance. So current would be 3 amperes. Now, if the current is 3 amperes, and if you look at this resistor, so if within this resistor, if I were to plug a voltmeter here, let's say there's a voltmeter here, the voltmeter says, okay, resistance is 2, current is 3. So I'm going to give you a reading of 6 volts, and that's understandable because see, think about what is volt. Volt is joules per coulomb. So every coulomb of charge that's coming out of this battery carries an energy of 6 joules. So that 6 joules, the entire energy is used here. Now, what is potential drop? Potential drop is when you're going from here to here, how much are you dropping? See, this is 6. So this was 6 volts here, this was 0 volts here. So as you walk through the resistor, you're dropping a potential of 6 volts. That's what the potential drop means. Now let's understand. Let's say what if this circuit I plug in another resistance. So let's say the circuit was this. So this was 2 ohms. And then you have the same battery here of 6 volts. But then what I do is I take another resistor of 1 ohms and plug it in here. So again, see, things are to be understood in a conceptual way. We are using formula here, but try to understand what's going on behind the scenes. Now this battery says, okay, I do see 3 ohms of resistance here. So says V equals IR. So I is V over resistance, 2 amperes of current. Okay, current is 2 amperes. From this perspective, can I say this would get 2 times 2, that is 4 volts, and this gets 1 times 2, that is 2 volts, right? So this gets 4 volts, it gets 2 volts, right? That's how the things work. So this one is 0 volts. I'll rather use another color here to kind of make it easier to understand. So this one is 0 volts, and the difference between these two terminals has to be 1 times 2, that is 2 volts. So if you were to plug a voltmeter here, it would say 2 volts. Now potential drop here should be 4. 2 times 2 is 4. So this is already 2. So difference between this point and this point has to be 4. This is already 2. This has to be 6. So this is 6 volts and that matches with this. So what's happening here is this keeps in 4 volts and this keeps 2 volts. And again, another way to visualize that is, so 6 joules of energy was coming out. Some of the energy is used here, some is used here because this is double the resistance. Because this is double the resistance, it's going to use double the energy. So this says whatever energy you use, I'll take double of that energy. So I explain it this way. So let's say there are two students, two kids, and there's a bundle of a bunch of jamun, my favorite fruit. There's a bunch of jamun out there, and one of the boys says, I would take double of what you take. So what you're going to do is you take that jamun and make three piles of it, right? Three equal, exactly equal, and give two parts to this person, one part to this person. Exactly, this is what will happen. This says I'll take double the energy than you. So you make three parts of it, 2 joules, 2 joules, 2 joules, give 2 times 2. So two bundles here. So that's 4 volts. So this one would take 4 volts and this one would take 2 volts. So basically this is how the potential drops work. And I am assuming you know all this. This was just a recap of this. Now the next point that you should know is ideal versus a real battery. So what we made just now was, so let's say what I did just now was, so let's say there was 6 volts of battery here. And I'm saying, okay, what if this is 3 ohms? I'm saying this battery is ideal. Ideal as in there is no resistance between the terminals of the battery. That doesn't happen. I mean, it's not an ideal world. There will be some resistance inside the cell or the battery itself. But let's say this is an ideal battery. This is an ideal battery. Ideal battery is the one where we are saying, oh, there is no internal resistance. So 2 ampere comes here, and this one would get the full potential of 6 volts because after all, whatever energy is being given here, it is being used here. But this is ideal battery. But what is a real battery? Real battery is the one which has some internal resistance. So what would happen is, so this was your battery. By the way, the battery looks something like this. A beautiful little battery out there. So this is what it is. But what is an actual real battery? Real battery is more like it has these two terminals, right? And then there is some internal resistance in there, some internal resistance in there. So this is how your battery would look like. It's all inside, so it's part of it. That's why it's called internal resistance. Now you're plugging in the same 3 ohms of resistance, 3 ohms over here. Now let's, for the sake of understanding, let's say this is still the 6 volts battery. So by the way, this 6 volts is called the EMF of the battery. It's the actual difference in potential between the two plates. Now assume that this is 1 ohms. I mean, it's not that big, but usually it's in decimals. But just for the sake of understanding, let's say the internal resistance were 1 ohms. Now what is happening in this circuit? This 6 volts part says, I don't see 3 ohms here. I do see 4 ohms. Isn't this like 3 and 1 in series? So it says I'm looking at 4 ohms here. So going by the Ohm's law, I would say V is equal to IR 6 by 4. So it is going to supply 1.5 amperes of current, and that 1.5 times 3 is 4.5. Wow. So don't you see, instead of getting 6 volts, this is now only getting 4 volts. So basically this is getting 6, this is getting 4.5, and this is getting 1.5. So what would happen here is, this was the terminal difference, the potential difference between these two terminals is only 4.5 volts. And this is called the terminal voltage. So potential difference between the two terminals, that is lesser than the EMF. And this is a real battery. So real battery was rated as 6, but in reality we're only getting 4.5 was of useful voltage out there. Does it really matter? So let's try to understand how that works. So let's say I had a battery here. So let's say I had a battery, and which was more like a real battery, and then it had an EMF of E. And then with that came bundled in one of the tiny little resistors, that's the internal resistance. And to make it easier to understand, let's make this like a battery. This is how the battery looks like. Now you connect this to another resistance of, let's say, uppercase R. This is your external load. So what would now happen? What would now happen is this says, I don't see R, I see R plus lowercase r. So it will say, okay, I'm going to supply a current of voltage divided by the resistance. This is the resistance. It's not R, it is uppercase R plus lowercase r. Now, what's available here or what's available here? There are two different ways to visualize. One is you can say what's available here is V is equal to IR. So this is I times R. So E times so what's available here? So let's make it. So if there was some voltage measuring device, let's voltmeter, it would say V is equal to IR. So it would say E times R over R plus R. So let me write it in a better way. So it would say E times R over R plus R. And you can see it's lesser than E because you're dividing by a bigger number, multiplying by a smaller number. So what's available here is less than E, and this is called the terminal voltage. Now you can visualize it using the Kirchhoff law as well. So let's call this point as P, and let's call this point as Q. So am I not interested in finding Vp minus Vq? That's same as this. So I'm interested in finding the terminal voltage, as in the potential difference between the two terminals of the battery. So if I think of that, so I start from Vp, and I'm traveling this way. So as I travel this way, I'm going from bigger plate to the lower plate. So I lose potential, I lose E. So I say minus E, and then I'm going against the current. See, note the current is going this way. So as I walk through the resistance, I'm going opposite of current. So current flows from high to low. So this one is higher, this one is lower. So I gain. How much do I gain? IR. So this was I, but for the sake of it, let me put it as I for now. So I'm gaining. What am I gaining? I'm gaining IR. And once I do that, I reach Q. So this takes me to VQ. So how much is VP minus VQ? Vp minus Vq is E minus IR. So you can clearly see the potential difference between the terminals is less than E. Now you can plug in this I over here, you end up getting this. So basically you can say the potential difference between the terminals is E minus IR, or you can write it like this, ER over R plus R. Either way, it's lesser than E. So internal resistance does matter, right? No, basically let's skip this slide. Maybe I'll go directly to a question and we can see how this works. So let's say a battery of 6 volts has an internal resistance of 1 ohms, right? So there's a battery of 6 volts. And let's make the battery. So let's say there is a battery here, and this EMF is 6 volts. This is 6 volts battery, and it has an internal resistance of 1 ohm. And I usually like to make it like look like a battery so that you can visualize, oh, that's all internal. So that's your battery. And then it's connected with a load of 4 ohms. So you take this battery and connect it to 4 ohms. You connect it this way. Now they're saying, what's the terminal voltage between this? So you can see what's happening here is you can directly use the formula or go logically here. So what's happening here is 6 volts is the EMF, and it says I can see 4 plus 1, 5 ohms of resistance. So how much current would it give out? So 6 divided by 5 is 1.2 amperes of current. 6 divided by 5, that's 1.2. And then you can say V equals IR here. So what are you getting here? So if you were to connect a voltmeter here, the voltmeter would say V equals IR, which is 4.8 volts. So terminal voltage, the answer is 4.8 volts. Or you can do it like, so terminal voltage is equal to E minus IR. Basically, both the things are same. So the terminal voltage is 6 minus, because this is eating up something. I is 1.2 times 1. So you get this. So basically, that's 4.8. So what is happening here is the external load is only getting 4.8, and the internal resistance is taking up 1.2 joules of energy. So 1 coulomb was carrying 6 joules of energy. Some was being used here, some was being used here. So here it is 4.8. Now comes the most important part of today, and that's why where we'll know how the batteries are, why the batteries are designed differently. And that's the main agenda today. But if you go through any book, I'm not talking about any publisher, you take any particular book, whatever author you like, it's given in a very difficult to understand manner. Maximum power theorem that people memorize, students memorize. So in simple words, what is it saying? It is simply saying that when you have a battery, and if this were R and this was EMF E, and you are connecting load here, resistance R. So see how some of the energy will be used here, some of the energy will be used here. The maximum power theorem says this will have its maximum power used when these two resistors match. I would repeat that again in simple words. The maximum power theorem, and we are going to prove it with say, common sense, no memorization, obviously. So what it is saying is this will have its maximum power dissipated when these two resistors are equal. And then let's go by common sense. First, let's go by common sense. So what does it even mean? Now, what is power? If you remember, power is I square R, isn't it? Power is I square R. We have done all these. If not covered, you can see my old videos. So power is I square R. Now let's make that circuit. So let's make the circuit here. And let's say this was internal resistance R. And again, this is very common sense. There's nothing to memorize here. And let's say this was uppercase R. And this was EMF E. So how much is the current? Current is E over R plus R, isn't it? E over R plus R. So that's the current and that's the resistance. So how much is the power dissipated here? The power dissipated here is equal to I square R. So this is this square times this. So E square over R plus R whole square. Right, I'm just doing I square times R. And now let's say I were to plot a graph. So let's say I were to plot a graph here, and the graph is, so what can I control here? See, this is a battery that is fixed. I purchased that battery and there's nothing much I can do to change that. It's just a battery that I purchased and it has particular EMF and an internal resistance. I'm not going to open that battery, change these parameters. What I can change is this. So this is my control variable. I can control this. So this is the independent axis. So where you can write the things that you control. I control R and I'm going to plot power with it. So I just want to know as I change resistance, the external load, how does the power vary? So let's start from the extremes. So what if when R, so let's pull this here. So when as R approaches 0, let's talk about when this is very small. If this were very small, think about it, there will be a lot of current, obviously, a huge amount of current. But as this approaches R, isn't this approaching a superconductor? So then it is not dissipating any heat. It's not using up that energy. A lot of electrical energy is coming in here. Common sense says that it is going to dissipate it as heat only when there is some resistance. I'm saying, oh, resistance becomes very small so that a lot of electrons go through that, carrying a lot of, like lot of coulombs are coming in, carrying energy on their shoulders, but there is no one to use it. If there's no one to use it, there is no energy anyway. So that's my common sense way. But what if I make this R very big? I say, okay, because resistance creates heat, I want maximum heat here. Let me make it huge. But as I make it huge, think about the flow of current will reduce now because V equals IR. So isn't the common sense telling me if you make this resistance very large, then yes, it is going to dissipate a lot of heat that it gets, but it's not getting any energy as such because amount of current will reduce. The amount of coulombs carrying those energy packets is going to reduce. So when the resistance is very small, then there is no point of thinking about dissipating any energy anyways. Then if the resistance is very large, you're getting less packets of energy. So either way, it's going to be very less power dissipated. There has to be a balance maintained between lot of current and bigger resistance. So that was more like common sense. Now let's go mathematically. So as R approaches 0, think about what will happen as R approaches 0. See, this is not how they explain in the books. That is the big problem. So as r approaches 0, can I say, okay, this approaches 0, this thing is dominated by this lowercase r? Because let's say this is 0.0001. I mean, there's no difference if I don't know, just remove this because it's approaching 0. So this is gone. This becomes r square. So don't you see the power is, so as this is becoming e square over r square, and as r approaches 0, power approaches 0. And then another way to visualize also is power is directly proportional to r now, because this is basically r square lowercase r square. So power is proportional to r. It's a straight line. So what will happen is at resistance 0, power is 0, and then as you increase resistance, it's more like a straight line path. Now, what happens when resistance approaches infinity? Wow, that's very, very meaningful. What would happen now is as this approaches infinity, as in it becomes huge. It becomes huge. What would now happen is, think about this one. This is huge. So then this lowercase r has no meaning. Let's say this is a billion and this is 5. So billion and 5 is same as 1 billion. So this lowercase r can be ignored in that case. So this basically becomes e square over uppercase r square times r square. So power actually approaches e square over r, isn't it? Because this becomes r square, this is r. So e square over r. So that basically means power is inversely proportional to resistance. And as r becomes huge, infinity, approaching infinity, power approaches 0. So when it is huge, it is 0, but then it is more like a curve, which is like inversely proportional. And at some point here, there will be the maximum power. So this is a common sense understanding that it's not like you make resistance less, so it will be more power, or resistance more power. There has to be some maxima out there. And this is exactly what we are trying to prove. So power is equal to E square over R plus R whole square times of R. Right. Now, when is the power maximum? What is your control variable? It is uppercase R. So you say for maxima, dP by dr is equal to 0. That is required for a maxima. So basically derivative of this. Now E square is basically constant. It can be pulled out. So you get E square d by dr of R over R plus R whole square is 0. Now this one will divide there and vanish. Now this is the quotient rule, kind of you write this as it is. So you write this r plus r whole square as it is, r plus r whole square times the derivative of this. Derivative of r with respect to r is 1, so there's nothing left there. Minus sign, then you write the numerator as it is, times the derivative of denominator, that is 2 times r plus r. Then over this whole square is equal to 0, but that again multiplies there and becomes 0. And you do this, and when you open these, so r square plus r square, let's do that. So r square plus r square plus 2 lowercase r uppercase r minus 2rr, the same thing that crosses out anyways, minus 2r square is equal to 0. Now this is a very elementary kind of calculation that crosses. R square minus uppercase r square is 0. So basically what you're getting is r is equal to r. So basically when the external resistance is equal to the internal resistance, it is the maximum power. Now why does it matter? Why does it matter is, usually think about it, you might have seen these batteries are used for more power devices, the bigger torches, those kind of things. And these are used for lightweight kind of things, like these remotes. So where you need less energy, you would use this. Where you need more, kind of, you use this. And one thing that comes to mind is, okay, it's big because there are a lot of coulombs filled in there, milliampere hours. So a lot of energy is stored in there. So that's why this is big. Yeah, that is true, because When you need more energy, you have to store more energy, bigger water tank. That's one reason to make this big, but there is more, something more that textbooks don't talk about. See, think about everybody is giving 1.5 volts, right? All of them are giving 1.5 volts, all your devices accordingly. Now, what is power? Power is I square R, VI, and all those. So, but I'll be using V square by R because for a given voltage, power and resistance are inversely proportional. So let us say there is a device here. There is a device, and that is, let's say, 10 watts. And there's another device, and that is rated as 50 watts. So think about it. Who will have a lesser resistance? More power, less resistance. So this one has a less resistance. So let me write it with yellow color. So this has less resistance, and this one has a bigger resistance. Now, what kind of battery would you need for this? You would need a battery so that this R, this resistance of this, matches the resistance of battery. Now, this small batteries, because of the size, they have bigger R. So this one has more R, more. So let me write it big. That big R. This one has a bigger resistance because of the size there. You have studied resistance, right? And this one has a smaller R. So see how they are designed in such a way that this battery will be used here, which needs a lesser R because its internal resistance is less, which is matching with the lesser resistance of this. And this one has a bigger R, which matches with the bigger R of this. So you see how these things go hand in hand. So let's say you have a remote which with a bigger R, it has huge R, and you think, okay, no, I'm going to use this battery by plugging in some wires. Yeah, this remote will work, but it's not going to work as efficiently as with this one because here it's going to be mismatch. Less R, oh sorry, big R. This remote has a bigger resistance. You're giving a battery with a smaller resistance. And same goes, I mean, if you were having a lesser resistance device and you say, no, I'm going to use this battery. No, that doesn't work like that because now the lowercase r and uppercase R will not match. So you can use it for some time, maybe just until you have another one, but these are optimized for the use of their own specific devices. So students, maybe this portion is never being asked in the examinations. None of the board exams, JEE exams is going to cover this, but think about, don't you think, if you agree, give me a thumbs up in the chat box and also write in the comment boxes if you're seeing the recording. Don't you think the physics has to be learned this way? We all study internal resistances, we study EMF, we memorize terminal voltage definitions. Why don't we relate it to our day-to-day life? It may not be asked in the exam, but that's how you learn physics. So now, honestly, tell me, wasn't it easy? If you like it, share this video, subscribe to the channel, and I'm going to get more of these videos very soon. So thank you, students, and please subscribe to this Telegram channel for more updates. And keep up the Josh always. Whatever is your dream, study, hard work, and Josh is going to make it possible. So see you soon, students. Bye bye. Love you.